Chapter 2, Part 4. So in this part, we're going to have inventory and reliability models. The ones that we had in previous parts, they were related to somehow the queuing systems. But in this part, we're going to see how we can simulate inventory and reliability models if some parameters in these problems are uncertain. Okay. Okay. Here we will have these models. At first, we will see how we can simulate a newspaper vendor model. Okay. You had this model in your previous course, MSci 334, and there you saw that how we can obtain the optimal solution for this problem in a simplified version, right? But here we will see more complex of version of this problem, and since it's complex, so we can't apply the optimal solution here, and so we will solve this problem through simulation. Okay, we'll see how it works. And also we'll have the MN inventory model, which is called order up to level. Okay, so again, we'll see how we do this in simulation. We had again this version of modeling, it is simplified version in MSci 334, but here we'll solve this problem in more complex version, I can say. I mean, some parts are uncertain, so we'll see how we can solve this complex version of this problem in simulation. Okay, and also for reliability, we'll see a model here, and we have more models here in chapter 2. Bomber hitting a target, explaining the distribution of lead time, demand, and also a project planning example activity network. So these models are some will be actually covered in tutorial session, and maybe was self-study, but I think, yeah, they are not self-study. In tutorial you will have all these models, but here and in chapter 5 I'm gonna actually cover the first 3 models: newspaper vendor model, MN inventory model, and reliability model. Okay, let's start the first model, news vendor problem. Here we assume a news vendor buys the papers for 33 cents each and sell them for 50 cents each. So there will be 17 cents per newspaper. Okay, and the newspaper is not sold at the end of the day, are sold as a scrap for 5 cents each. Okay, and so newspapers can be purchased in bundles of 10. So here we have bundles of 10. It could be, for example, 10, 20, 30, 40, 50, 60, and so on. Okay, and so there are 3 types of news days. Yeah, based on the demand of the days, we can categorize the days for 3 types. So it will be good, fair, and poor. Okay, so in terms of the demand quantity, we can say a day is a good day, then we will have a higher demand for newspapers, right? Or if it's fair, somehow the demand is somehow in medium quantity, or if we have very low demand on a day, we call that day as a poor day, right? So yeah, we have these 3 types for day in terms of the demand for newspapers, and these are the probabilities for having these days. Based on the historical data, we have observed that in 35% of times a day can be a good day, or in 45% of times a day can be a fair day, and just in 20% of times a day is a poor day. Okay, so we have the probability like this, and here you see the demand for each type of the day. Demand can be any number between 40 to 100, and not any number. Here we assume that a bundle of 10, so it will be 40, 50, 60, 70, 80, 90, and 100. Okay, and as you see here, we have these 3 types of the days, and we have the probabilities for demand quantity on any type of day. Okay, so this is the reason that here we call this problem much more complicated than the one that you had in the course MSci 334, right? As you see here, we have 3 different types of the day, and we have the discrete probabilities. So this problem cannot be solved by the optimal solution approach, right? So here we have to actually apply the simulation in order to find the optimal solution, or a good solution, actually, not optimal solution, a good solution for this Nussbender problem. Okay. So this is our question that we are going to answer this question by simulation. Compute the optimal number of papers. Yeah, optimal number of papers the user science should purchase by simulating the demands for 20 days. Okay, so this is our question, and as you see here, we are asking about the optimal number of papers. So how can we obtain the optimal number of ordering through simulation? So just think about it for a few maybe seconds or minutes, but you will see how we do this, okay, in simulation. Okay, so we are going to actually obtain the optimal number of papers by simulating the demand for 20 days. Okay, 20 days. Okay, and our actually objective function here, in order to optimize the number of papers, is somehow maximizing the profit, right? And the profit is calculated by this relation. So we have a revenue from sales, right? And all newspapers are purchased for 33 cents, right? So we have the cost of newspaper, and we have lost profit from excess demand. So we may have excess demand, or we may have excess quantity in inventory, right? So if we have excess demand, so we have lost profit, or if we have excess quantity in inventory, so we will have salvage value for the scrapping of those papers, right? So yeah, by this function, we can calculate the profit for each day. Okay. So let's define the notations that we need to define to model this problem. The first one is Q, the order quantity. Okay, so the order quantity that Nussbender should consider for ordering newspapers at the beginning of each day. Okay, and the number of days here is 20 days. So we are going to simulate the problem for 20 days, and we can define the type of day by Ti and demand of day I by Di, and sales on day I. So sales could be this: if demand at day I is less than or equal to Q, our quantity, then sales will be equal to demand, right? Other than that, it will be Q. Okay, and revenue on day I will be just this, 50 cents times the sales amount, right? And the lost profit from excess demand could be this. So we are losing 17% for any lost sale. So the lost sale, if demand is greater than or equal to Q, so we have lost sale, right? And it will be Di minus Q. Other than that, the lost sale will be 0. So by this relation, we can compute actually the lost profit. Okay, and the salvage value when the quantity is greater than or equal to the sale of at each day, right? Then Qi minus Si will be at the excess inventory at the end of the day, and we need to scrap this one with 5 cents. So this will be the salvage value or scrap value at the end of the day. Okay, And so the profit will be this: RI revenue minus 0.33 Q, the purchase price for the Q, minus LI, the lost profit, plus SI, the salvage value. Okay. And these are the steps to simulate this problem, news vendor, news dealer problem. At first, we initialize I by having I equals 0. So we start from 0, and N will be 20 and Q. So this is where I asked you actually to think about how we are going to optimize the order quantity. So as you see here, for running the simulation, we need to consider a value for Q, right? It can't be a variable in the model. And we need to assume this a quantity, a value. So yeah, I mean, any run of simulation will be based on a given Q, right? So this is how it works. We need to try different values for Q. So we know that the demand per day varies between 40 to 100, right? So we can actually assume that Q can be 40, 50, 60, 70, up to 100. And for each value of Q, we will run the simulation model. Okay, and at the end, we'll see which value for Q generates more profit, higher profit, and then that will be the optimal value of Q, right? Yeah, as we had in chapter 1, I guess, yeah, in chapter 1, we studied that our optimization are based on the alternatives that we consider for simulation runs, right? So here we assume a certain values, a discrete values, I mean, from a discrete set, certain values for Q, and then based on those alternatives, I mean, that we consider for Q, then we can find the one with the higher profit, and then we will consider that one as our optimal solution. But we know that this is not really optimal, right? But yeah, we can say that just it's a good solution based on our experiment, and that's it. Okay. So then by having a given Q here, we generate TI and DI, type of the day and demand, and then we can calculate SI, RI, LI, and SI based on the Q and T and demand, right? Then we can calculate the profit of the day, and we check the desktop condition here, and then we can actually replicate the simulation for 500 applications. Okay, yeah, here we are simulating for 20 days, and then we can replicate the simulation of 20 days for 500 replications, 500 times. At each time, it will be a simulation for 20 days, right? But by replication, we are somehow decreasing the impact of uncertainty, right? So yeah, so then because of that, we can say somehow if the Q is 50, for example, 60, 70, 80, 90, 100, then we can consider those values, one of these values, as the optimal solution for the problem. Okay. So you will see in the next part the implementation of the news vendor problem in Excel, and you will see how it works in Excel and how we can obtain the optimal value for Q. Okay, so let's go for the second problem here, the order up to level inventory policy MN. So as you see here, here actually we consider a constant period for ordering. So this means that we're going to order every n days or every n periods. Let's say here our time unit is days, so every n days we are going to have to place an order, right? And the quantity of the order in that time will be the difference between actually the M our maximum inventory level and the current inventory level at that time, and then we will order up to M level. So it depends. So the quantity of ordering will be actually different at any time at the end, and it depends to the level of inventory in that time, right? For example, here we will order this amount, but here we order this amount, right? So this is called actually the order up to level, okay? And this is a policy in inventory control, and it's called MN policy, okay? So here M is the maximum inventory level, N is the review period, so it could be the number of days or hours or weeks or month and so on. And Q is the order quantity, and L is the lead time for ordering, okay? So let's have our example here. Here we assume a company is selling refrigerators and the review period for ordering is N days. So the company will review an inventory every N days and make decisions on inventory. I mean, obtains the quantity of order, okay? And the policy is to order up to the level M, okay? So the order quantity here will be this. Ordering up to level M, it's given minus the ending inventory. It depends on the ending inventory on that day. I mean, every end days. So in that day, what is in the ending inventory will be here plus shortage quantity. Okay, so by this equation, we obtain the order quantity. Okay, so the number of refrigerators demanded each day is a random variable. So yeah, demand of refrigerators each day is a random variable, and the lead time also to receive the order quantity from supplier is a random variable as well. Okay, so this is for demand. As you see here, demand on each day could be 0, no demand, 1, 2, 3, and 4 refrigerators. And these are the probabilities and the CDF function. Okay. And the lead time could be 1 day, 2 days, or 3 days. Okay. 1 day, 2 days, or 3 days. And these are again the probabilities. Okay. So orders are placed at the end of the day, say Monday. So any day that we are going to place an order, it will be happen at the end of the day. Okay. So if the lead time is 0, actually we don't have this case because we know that lead time varies between 1 to 3 days. But if just in order to understand the discipline here, if the lead time is 0, then order will arrive the next day. Why? Because we are placing the order at the end of the day, and let's say it's 0, this means that we are going to receive right away the order, right? But since it's at the end of the day, we can't distribute this to inventory, and the distribution to inventory will be occur at the beginning of the next day. Okay. And if the lead time is 1 day, when the first option actually, then the order will arrive on the second day. So what it does mean? This means, let's say we are ordering at the end of Monday, then lead time is 1 day, right? It takes 1 day. So this means we will receive the order at the end of Tuesday, right? And again, it will go to inventory for sale at the beginning of the Wednesday, right? So as you see here, the lead time is 1 day, but actually takes 2 days in order to have that order in inventory for sale. Okay, because we are ordering at the end of the day, and that's the reason. Okay, so here we're going to simulate the system for having M as 11 and N as 5 days. Again, these are given here, right? We are assuming that the maximum inventory level is 11 and the number of periods that we are going to review the inventory for ordering is 5 days. They can be changed, right? So we may try different values for m and n, and then find the one which actually generates better performance in terms of the inventory cost, right? Then we can say that's optimal. But we know that it's not actually optimal because we are not going to try infinite number of alternatives, but because we are trying just certain numbers and from a discrete set. So among those alternatives, the one will be a better one, right? So we call it as optimal, but we know that it's not really optimal, and it's just a good solution based on the experiments, okay? So here we have our assumptions. Ending inventory on the 5th day of the cycle is 3. This means for the initial status, when we are going to simulate the system from time 0, so this time 0 will be the end of the previous cycle, I mean the 5th day, right? And we assume that the ending inventory in the previous cycle is 3. So in initial status for the system, we assume that we have already 3 refrigerators in our inventory, okay? And here we assume that the order size is 8 refrigerators, I mean in previous cycle, not now. This is time 0, and since we are going to order every 5 days, so this means at the end of the previous 5 days, I mean the 5th days, right, before time 0, we have placed an order, right? And it's here we assume that its order size is 8 refrigerators. So this means we have 8 refrigerators on the way as pending order, okay? And we assume that the lead time for that order is 2 days, right? The order that we have placed at the end of the 5th day in the previous cycle, the lead time for that order is 2 days, okay? So, and day 1 here, I mean, time 0 will be the beginning of the day 1, right? Day 1 of the new cycle of 5 days, okay? So the question here, find the average ending inventory for 5 review periods or 25 days. So here we're not going to optimize the order size and the value for review period and the number of days that we are going to review the inventory and place order. So we assume that we have these ones for a specific value. I mean, we have the specific value for these ones, m as 11, n as 5, and here we are just going to obtain the average ending inventory for this policy, for this assumption for 25 days or 5 periods, okay? But if we want to somehow optimize the values for m and n, then we can try different values for m and n and obtain the average ending inventory, and the one with a less average ending inventory will be the better one, right? And the notations here, we define the inventory cycle of the clock day I as Ci. I mean, it is the cycle. I mean, if Ci is 1, this means that we are in the first 5 days or the first cycle out of the 5 cycles that we are going to simulate in our simulation, okay? And day within the inventory cycle is Ni. So let's say Ci is 1, this means we are in the cycle 1, and then Ni is 2, this means we are in the day 2 of cycle 1, okay? And ith day beginning inventory will be Bi, ith day demand Di, ith day ending inventory Ei, ith day shortage quantity if we have Si, and ith day pending order. If we have order on the way as pending order, then we show this here by Pi. And the lead time of the order as on ith day will be Li, and the remaining lead time on ith day will be Lci. So by these notations, we can somehow model this problem and can implement it in Excel, okay? So let's have this steps of simulation of this system. At first, we have the initialization. And so in the first step, we calculate the ith day beginning inventory. So as you see here, the inventory at the beginning of day I will be equal to the ending inventory of the previous day, plus if we have a pending order and the number of days remaining in lead time 2 days ago was 1, then we will have that pending order in the inventory at the beginning of day I. Other than that, there will be no more item than the previous days in the inventory. So let me show you how this works. Here, assume that we are on day I, right? So this is I minus 1, this is I minus 2. So let's say here at I minus 2, we have the PI minus 2, a pending order, right? And here we assume that the LC, I mean, the remaining days in inventory in lead time is 1. So here we are at the end of the day, right? This is the end of the day, right? And it takes 1 day in order to have this quantity, I mean P I minus 2 in our system. So since it takes 1 time, so at the end of day of I minus 1, we will have this order in system, right? But this is the end of the day, right? Again, this is the end of the day. So since it's end of the day, so at the beginning of the day of I, so beginning of the day of day I, we will have that quantity in inventory, right? So this is why we have this if condition here that remaining lead time 2 days ago if equals to 1, then we will have PI minus 2 in the inventory at the beginning of day I. Okay, so and then we generate the demand of day I, and then we can calculate the ending inventory of day I. So as you see here, if demand of day I plus the shortage of the previous day, if we have these two, if these two minus BI, the beginning inventory, then if this equation is, is less than or equal to 0, I mean it's negative, then then ending inventory will be BI minus DI minus SI minus 1, right? Or if demand of this day and the shortage from previous day minus the inventory at the beginning of this day is positive, then DI plus SI minus BI will be the shortage at the end of this day. Okay, and for computing the pending order on day I, we have this equation here. So if the day is the last day of each cycle, I mean we are on the last day, the 5th day of each cycle, then it's obvious that the pending order will be 11 minus EI, right? 11 as the maximum inventory level minus the ending inventory level at this day. 11 minus EI, sorry, plus SI, the shortage if we have. And if not, again, if the remaining days on the lead time equals 1, then there will be no order. I mean, no pending, because we have already received that. But if it's not equal to 1 and it's greater than 1, then we have a pending order, and the quantity is PI minus 1, right? So, and compute the lead time LI for the order PI if there is a new order, yes. And remaining lead time for the pending order, again, we have this. If the number of day on the cycle is the last day, it equals 5, then the remaining of lead time will be exactly the lead time, right? LI. Other than that, if LCI minus 1 is greater than 1, then it will be LCI minus 1. Minus 1 because we have passed 1 day from that day, from I minus 1. Other than that, it will be 0. Okay. And yeah, this is the stops condition. If we have a simulate for 25 days, we stop. Other than that, we repeat steps 2 to 8. Okay. So more discussions on the inventory models. This is a self-experiment. By having the models in Excel, you can try these scenarios. For example, define and derive various statistics for the inventory models, like average ending inventory, average demand, number of stock outs or shortages, for example. Or for example, for news vendor problem, what if the salvage value increases? Let's say becomes 10 cents, and then what will be the impact of this change on the model, on this performance of the system? And what if we consider the number of days to simulate, let's say increase the number of days for simulation, let's say 100 days, and will it give better insights? So let's try. And for MN inventory model, again, what if we increase M and reduce N, or we reduce M and increase N? And again, what will be the impact? So we can actually analyze the impact of all these changes on the system performance by having a simulation model. And since you have the model in Excel, so you can try all these ones to see what are the impacts. Okay, thank you.